Alright guys, welcome to Synthetic Division. We are going to show you a faster way of doing long division, but we're going to do it with a technique called synthetic division, which I promise you're going to love, and you're going to be really disappointed when you don't get to use synthetic division. Alright, so let's just review long division really quickly. You would ask yourself, how many times does x go into 7x to the fourth? You put that number up on top, distribute through, subtract the rows. Then you ask yourself again, how many times does x go into 3x to the third? Put that number on the top, distribute all the way through, subtract the lines. How many times does x go into negative 3x squared? Put negative 3x on the top, distribute all the way through, subtract the lines, and a final time, how many times does x go into negative 10x? Put negative 10 up on top, distribute all the way through, subtract, and we have no remainder left over. That's how long division works, right? Yes. So, my question for you though is, can you do it without the variables? The variables are just kind of getting in the way here. What I really care about are, what are the coefficients? What are the coefficients to all those terms? So if I took away all of the variables, can you still do long division? All right. Now imagine I've got an x hanging out in front. You can see up, but you can cheat if you need to by looking up in the top left corner. But imagine I've got x minus 2 hanging out here. The first thing I'm doing is I'm saying, well, how many times does x go into those 7x to the fourths? 7 up on top. 7x to the third goes up on top. But again, don't worry about the variables. Just put a 7 up there. You would distribute all the way through. Then you'd subtract those two rows. Then you do it again. How many times does x go into 3x to the third? Oh, well, 3 times. Put a positive 3 up on top. Distribute all the way through. Subtract those two columns, then do it again. How many times does x go into negative 3x to the second? Negative 3 times. Well, negative 3x times. Negative 3, distribute all the way through, add that, subtract that column. That's negative 10. Do it one more time. How many times does x go into negative 10? Negative 10 times. Distribute all the way through, and then I'm subtracting that last column and getting no remainder. I just did the exact same thing, but I did it without the variables, because really the only thing that's changing, I know where the variables are, the only thing that's really changing is the coefficients. All right. Pro tip, you can actually make this a little bit more compact. You can make it take up less space. And you just hold on to your horses here. We are almost at synthetic division. It's a really compact, streamlined way of doing long division. All right, what I want you to notice here is that the bottom row is the same thing as the top row. Well, except for the 7's missing in the front, but we can fix that, right? Do you see, like, it's 7, 3, negative 10? Look, well, let's just go ahead and just copy that 7 down at the bottom. 7, 3, negative 10. If you just copy that 7 down, you just have to look at that row. On the bottom, those are the coefficients of your answer, right? And again, I had no remainder over there. So you just, you can strip out the variable, and you can only focus on the coefficients and come up with the exact same answer, right? Those are the coefficients of your answer. You can actually even do yourself one better by changing the sign of the divisor. If you change it from -2 to +2, then really, this row on the inside, you just change those signs. That's going to have the effect of changing those signs so that you're adding the columns instead of subtracting, right? Your brain is actually really good at multiplying and adding. Not so good at finally subtracting, as we've seen probably in class. So let me show you what this looks like from the beginning, right? If I have some polynomial and I want to divide by x minus 2, I'm going to put x plus 2 in the box. And here's the technique. I grab the leading coefficient and I just copy whatever it is, I just copy it below the line. Any number that goes below the line, you multiply by the number in the box. So 7 times 2, that goes 14. Now I'm going to add those two columns. I get a sum of 3. Multiply by the number in the box, that's 6. Add that column, negative 3. Multiply by the number in the box, add that column, multiply by the number in the box, add that column. You guys will have the exact same set of coefficients with no remainder, and all you have to do is just put the x's back into it. right? I knew that I started with a quartic equation. So by the time I divide out by x minus 2, I'm going to be left with a cubic equation. The degree just goes down by 1, right? But you can just put the 7, the 3, the negative 3, and the negative 10, just slap that on into the as the coefficients of your quotient. It's pretty slick. So let's do another example. Here's a polynomial that I deliberately created so it had a whole bunch of factors, right? We can divide by any of those factors and end up with 0 as a remainder. There's actually one factor that won't work for synthetic division. Can you see which one of those might be a little bit different looking? That's right. A factor where the leading coefficient is not 1, you can't use synthetic division on that, unfortunately. I'll post an enrichment link that shows you how to, like, one technique for handling that, but it's honestly, it's more trouble than it's worth. At that point, you're probably just going to want to do like long division or tabular division, right? But the other ones should work fine. So let's try it. Take the polynomial, divide by x plus 4. Watch how fast this is. If I want to divide by x plus 4, I put minus 4 in the box. Then my leading coefficient, it comes down, multiplies by the number in the box, add that column, multiply by the number in the box, add that column, multiply by the number in the box, add that column, multiply by the number in the box, add that column. Done. There's the coefficients of my quotient. And again, I have no remainder. So you just put the x's back in, you're done. This is a pretty fast way of doing things. All right, let's do it again. Let's divide that polynomial by x minus 2. I'm going to put plus 2 in the box. I'm going to drag my leading coefficient down, multiply by the number in the box, add, multiply, add, multiply by the number in the box, add, multiply by the number in the box, add. There's my coefficient. There's the coefficient. Those are the coefficients of my quotient. You just put the x's back in and you're done. Pretty slick, huh? Is there always a remainder of 0? No, of course not. You can divide by anything you want. Those just happen to be the 4 values that would give you 0 remainder. But you can divide by other things. Like if I divided that polynomial by x plus 1, I could put minus 1 in the box, copy down my leading coefficient, times the number in the box, add that column, times the number in the box, add that column, times the number in the box, add that column, times the number in the box, add that column. This time, there's my quotient, but this time I have a remainder of 27. So that's so how do you write a remainder of 27? I think we've already talked about this in class, where I think back in 3rd grade you would write R27 or something like that, but eventually you learned how to write remainders as fractions that still need to be divided by the divisor. So we're going to do the same thing here. We're just going to write that quotient, that remainder, as 27 over x plus 1. I think about it as I have 27 bits left over that I still want to divide by x plus 1, but I can't. So that's what my remainder is. All right. 27, I just want to stay here for a second because I'm going to try and show you the other, this is the other benefit of synthetic division. Synthetic division, 27, that remainder of 27 happens to be the value of the function when x is equal to -1. So the other really huge benefit of synthetic division is that synthetic division is a really fast way of plugging in values and getting answers. Like if I needed to evaluate this function in the numerator here at x equals -1, you can either plug in -1 to that function and just like try and deal with all those signs, type it into your calculator, blah, 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 blah. You know, if you do synthetic division by putting -1 into the box, the remainder is the value of the function. It's so much faster. You can be done with synthetic division before you even find a calculator and type that expression in. That's called the remainder theorem, and we can probably talk about that in class a little bit, all right? But plugging the x value into a synthetic division box, the remainder that you get is the value of the function there. It's really cool. All right, so there's a bonus question for you. If you happen to divide by something that divides the polynomial perfectly, like by one of its factors, there shouldn't be a remainder, right? The remainder should be 0 if it divides evenly. So do you remember when we divided that polynomial by x minus 2 and we got no remainder? Well, guess what the value of the function is when x is equal to +2? Guess what the value of the function is? Do you see it right there? It's right there. It's 0. because it divided evenly. I'm hoping things are connecting for you in your brain. All right, here we go. So in a nutshell, regardless of whether I'm asking you to do polynomial division or evaluating a function at a certain value, you can use synthetic division and come up with, and it's one and the same, right? Whether you're dividing by this polynomial by x plus 3 or trying to evaluate the numerator when x is equal to negative 3, regardless of your goal, you can slap negative 3 in the box and just do the synthetic division trick. The 2 comes down. We're going to multiply by the number in the box, add that column, multiply by the number in the box, add that column, multiply by the number in the box, add that column, multiply by the number in the box, add that column. There's my quotient, and there's my remainder. All right? And that also happens to be, that negative 35 remainder, also happens to be the value of the function when x is equal to negative 3, right? So, some more practice. I'll do a couple more examples. Some things that always come up at this point. What if the leading coefficient of the divisor isn't 1? What happens if you're trying to divide by something that's not x plus 3? What if you're trying to divide by 2x plus 3? And the answer to that is no, don't use synthetic division for divisors that have a leading coefficient that aren't 1, right? We'll talk about that later, or maybe I'll post it in the enrichment. These other two questions we should be okay with. What if you're missing some terms, right? Like what if you're missing the cubic term and you need to divide by x plus 4? And then we'll, does it also work if you throw in divisors that are like imaginary divisors? Spoiler alert, it still works. All right, let's talk about the missing terms thing though. This is something that will come up for you, I promise. When you try and divide x plus 4, 3x squared minus 4, notice that I'm missing the cubic term. There is no x to the third term, and notice that there is no x to the first term. So when you go to do synthetic division, you list those coefficients, you can't just write 1, 3, and negative 4. You need to use zeros for placeholders where there are missing terms, all right? You gotta keep these things all organized in terms of decreasing, descending powers of x. So if there isn't a cubic term, you have to write 0 in there as a placeholder so that nothing gets messed up. All right, same thing over here. The linear term, there weren't any x to the first power, so I'm using 0. But as long as you're putting zeros in as those placeholders, everything works out just fine. Copy your 1 down, multiply by the number in the box, add, multiply by the number in the box, add, multiply by the number in the box, add, multiply by the number in the box, add. There's your polynomial quotient, and you have a remainder of 300, which is also happens to be the value of the function at negative 4. So yeah, you just put the x's back in and you're done. All right, my last example for you is I just wanted to show you that this even still works even if the divisors are really strange looking, like x minus 2i. This synthetic division still works. You can still list your coefficients, put 2i in the box, and carry your 5 down. Multiply by the number in the box, add. I know, that looks weird, doesn't it? But you added them. You can still multiply that by the number in the box, add that column, multiply by the number in the box, and add that column. There we go. We're probably not going to ask you to write the actual polynomial here. I mean, that's going to be a goofy looking polynomial, as you can see. But the important part here is that 0 is a remainder. 0 was the remainder. So what that means is that 2i is one of the solutions to that equation, that cubic equation. 2i is one of the values that you can plug into that expression and get 0 as an answer. All right, this is going to come back later. All right, so with that, you're going to try these on your own. We're going to talk about them in synchronous time to make sure that you guys things are making sense. Try these on your own before class starts. To make sure that you're on the right track. The answers to 1, 2, 3, and 4, when you do the synthetic division, the remainder that you get will be the same as the problem number, right? So give it a shot. We'll talk about it in synchronous class. See you then.